Hello friends, let's continue with the structures in chemistry in everyday life. In the last video, I've stopped at tranquilizers. Now let's continue with analgesics. So here we have two types of analgesics, non-narcotic analgesics and narcotic analgesics. Under non-narcotic analgesics, we have aspirin and paracetamol. These structures are not there in chemistry in everyday life lesson, but it's better for you to remember them. Okay, so salicylic acid is basically you draw benzoic acid and then you attach this group like this. This is self-explanatory. And similarly, this paracetamol, N-acetyl, para-aminophenol, you draw phenol and then you should be replacing hydrogen of this carbon with this group. Okay, so these structures need to be memorized as they are. Next, we go to narcotic. Now, under narcotic, we have three examples: morphine, heroin, and codeine. How would you draw this structure? So first you draw hexagons like this. Okay, something like honeycomb, you could say. First you will draw three hexagons like this attached at their sides. Next, using this 1, 2, and 3, you would be drawing a 5-membered ring with oxygen here. Okay, 1, 2, 3, 4, 5. Next, we aim to draw a 6-membered ring. This is a 6-membered ring actually. You can count from here: 1, 2, 3, 4, 5, and 6. So this is a 6-membered ring. If you think that this is in the plane, then this is in the air. This part is in the air above the plane. Okay. So N and a methyl group attached to nitrogen, and okay, the group here. This is one end. Don't get confused with this part over here. Okay, by mistake it has got mixed with that point, that carbon, and here like this. So now here also 1, 2, 3, 4, 5, 6. Okay, now this is benzene, and here you will be drawing a double bond. Here there is G1 group, and you know what is G1, and here this is G2. Now if G1 and G2 are both hydroxyl groups, then it is morphine. If G1 and G2 are both OAC, then it is heroin. If G1 is OCH3 and G2 is hydroxyl group, then it is codeine. Okay, so once you know this structure and once you know what is G1 and G2, this memorization shouldn't be tough. So let's go to the next part. We have antimicrobials here. Under antimicrobials, we'll first deal with antibiotics. So first we'll start with so Paul Ehrlich, first he discovered salvarsan. Okay, so salvarsan structure is something like this. So what you'll do is AS double bond AS, and if you see this part and this part are same, so you could learn one of them and the other part you could just attach it. Basically the structure is symmetric, so you can learn how to draw this structure, and later he found that this structure has similarities with azodine. So using this analogy, he developed what is called Rontosil. Okay, so azodine, you might be familiar from reactions involving diazonium salts, and from here this structure is important. So how will you draw the structure? So you first draw doubly bonded nitrogen like this, double bonded nitrogen, and then like this benzene group attached like this, and exactly opposite of this carbon, replace hydrogen with this group, NH2. Okay, next come to the other side of this double bond, and then you will be drawing benzene again, and exactly opposite of this carbon, replace hydrogen here with NH2. Okay, and at this position and another NH2. So basically, as you can see, you have to memorize the structure as it is. Okay, this is just a way of doing step by step, drawing the structure step by step. Next, we go to other set of drugs, which are sulfanilamide, sulfapyridine, sulfonamide. Okay, if you can observe, this part is same in all the structures. In this three types of drugs, this part is same. Okay, learn this part somehow. Learn this part. You will be drawing a benzene here, and then replacing hydrogen with NH2, and then replace the consider carbon exactly opposite of this carbon, and then replace this hydrogen with sulfur group like this, and NH. Okay, now here what you keep changes So based on what you keep here, the drug will be named accordingly. So suppose if you keep hydrogen there, it will be called sulfanilamide. If you keep pyridine in a certain fashion such that here the carbon adjacent to nitrogen of pyridine must be connected here, then it will be called sulfapyridine. Or if it is normal R group, alkyl group, then it will be called sulfonamide. Okay. So let's go to the next part. Here we have penicillin and chloramphenicol. So basically for drawing penicillin, first draw house. So here first you draw a house, something like this. It's not exactly a house, but yeah. So at the top of the house put S. Okay. Yes. Then at this junction put N. Okay. N. And here. So this is basic thing here. If you can see, this is it. And put two antenna like this. If you can think, it can help. And see which this part you should remember. Here there is hydrogen, the extra parts. This you are supposed to remember as there. And here you would be drawing a normal amide group. Amide group like this. Okay, NH, of course, NH. So this is the structure of penicillin. Now coming to chloramphenicol, if you just see the structure, it is somewhat like this. And here there is something. Okay, this basically looks like some tongue. Okay, what you will be doing is first connect two chlorines to a common carbon like this. Okay, then you draw a straight line, then doubly bonded oxygen you connect it to this carbon in this fashion, and then nitrogen and like this OH and OH. This is pretty much self-explanatory. And to this carbon here, you will be connecting a nitrobenzene in this fashion, such that the carbon opposite to the carbon containing nitro group is attached to this carbon. Okay, this completes chloramphenicol structure. So you can remember for chloramphenicol, this chlor implies that there is some chlorine in the molecule, and you could just remind yourself about this tongue-like structure. Okay. Next we go to antiseptics. So here we have chloroxylenol, terpineol, and beta-enol. Chloroxylenol and terpineol are together called as Dettol. Okay, and this is just a fact-based info. Next, here in chloroxylenol, the name itself has a lot of information about this structure. So chloro implies that there is some chlorine in the molecule. Just for remembering, say, chlorine is there in the molecule, and then xylene. If you can see, if you replace for drawing the structure of xylene, take benzene and replace hydrogens of any two carbons with a methyl group, then you get xylene. So this is xylene. Or based on the relative positions of these two methyl groups, you could have ortho, meta, and para xylene. Okay, so here we consider metaxylene. Okay, between these two methyl groups keep chlorine and then OH. Okay, OH. This all also now it should give you an idea of hydroxyl group being present in the group in chloroxylenol. So this explains the structure. In terpineol, there is nothing much to remember. Just there is nothing much to explain. You just have to memorize it as it is. So maybe could draw like this, as though this looks like a stand. OH like this, and then this. Don't forget to keep this double bond here. Okay, like this. Okay. Similarly, beta-enol structure is self-explanatory. This itself is very simple, and you can draw it. Okay, that completes our antiseptics. Now coming to anti-fertility drugs, these structures, if you really want to learn them, then you have to mug up as they are. But how I have shown narcotic analgesics, similarly here you draw rings attached to each other in this fashion. Okay. 6-membered rings, and here for this as base you draw a 5-membered ring. Okay, like this. Okay. And now from here, consider this position, and this position. Alternatively, put hydrogens above and below the plane. So from here, the hydrogen is above. Next, it will be below. Next, it will be above. Next, it will be below. Okay, this set. So now you know how to keep hydrogens here. Okay, and then you have to place above the plane methyl group here in this fashion. Just remember, and similarly OH group, okay, OH group, and then below the plane this ethynyl group, like this. Sorry, CH. So and of course here a double bond. Okay, this part is same for both the structures. If you attach doubly bonded oxygen like this to this carbon by replacing its hydrogens, then you'll get north and drone. This own should give you an idea of oxygen being doubly bonded to this carbon. And here similarly ethynyl estradiol, which is estrogen, this old should give you an idea of alcohol being like this. Okay, so this is the difference. If you can go one step further, you can think that between these two structures, from north in drone, if you want to get ethynyl estradiol, you just add a double bond here, just for the sake of remembering, so that this will tautomerize and it will result in an aromatic ring, which is this itself. So you can remember it in this fashion also. Draw north in drone and add a double bond here, and then tautomerize this. After tautomerization, you'll get ethynyl estradiol. Okay. Next, we have artificial sweetening agents. So here we have aspartame, saccharin, and sucralose and allicin. So here in the structure, ASP and PHE represent the R group corresponding to the amino acids with this notations. In biomolecules chapter, you have general structure of amino acids with R present in it, and for different R, you'll get different amino acids corresponding to that R. I have drawn here. In order to avoid confusion, I have drawn the actual structure of aspartame. Okay, so this is a peptide bond. So this is so the structure is self-explanatory, and don't forget to add a methyl group here. Okay, methyl group like this. It becomes an ester. Okay, and saccharin. The structure you have to memorize it as it is. There is pretty much nothing as a hack to remember it. Simply draw and draw here, attach the groups here. Yeah. Next we go to sucralose and allicin. So here, first let me cover allicin. In allicin also, this ASP and ALA correspond to the R group of amino acids. These are not amino acids in themselves. They correspond to the R group present in the general structure of amino acids as discussed in biomolecules chapter. To avoid confusion, again I have drawn this structure, and this is a peptide bond again. And here, if you can see here, there is NH and this group. It's very easy to draw and remember also. Put sulfur here and then things like this, and then connect like this, and then you have the rest of the structure. One thing to note is that in allicin you have N here, okay, NH group, and then it is connected to some other group. But in aspartame, here you have oxygen. This part you should be remembering. Next, coming to sucralose, you could actually mug up the structure like this, or since sucralose kind of relates you to sucrose, I have made changes in the structure of sucrose, like what changes you have to make in sucrose in order to reach sucralose. So whatever is there in dark blue and orange over here represents the structure of sucrose. So if you replace the hydroxyl group present in sucrose with chlorine here, and similarly here with chlorine, and similarly here hydroxyl group with hydrogen, and here hydrogen with chlorine, then you get the structure of sucralose. Okay, these 4 changes you can remember at this specific hydroxyl group positions, this part and this part. If you can remember this, then sucralose structure is just a cakewalk. You can get it very easily. Here you could remember in another fashion. You could replace the hydroxyl group by chlorine and then invert in the sense you bring the hydrogen down here and chlorine back up, then also you would be ending up with this structure. Okay, that completes the video. So you can make, I hope you are all motivated to learn this, because on seeing it at first time, the structures look very difficult, but I hope you are motivated now. Thank you.